Hello everyone and welcome to this new video in which we will continue our discussion about the assembly language. And again, like we did in the last two videos, this will be also a video in which we will not code yet, but we will talk about some important facts about computer architecture because we will need them in the long run. And in fact, the next video will be the first video in which we will actually start coding. So in today's video, we will start by talking about how do computers work. So what is the architecture of a computer? And the architecture of basically nowadays any stored program computer, and we will also talk about what I mean by stored program computer more precisely, is what it's usually known as the von Neumann architecture. And it is basically a model for the architecture of a computer. So how do computers, all the computers that you nowadays use, how do they work? A computer has five basic parts, and these five parts are: number one, that's input, output, then we have memory, then we have control, and data path. So now you probably are familiar with some of these words, but maybe some of them might sound a little scary. For example, I'm sure you're familiar with the words input and output. And input is fundamentally just what you put inside the computer, so the data you insert in the computer in order to make it process. So we could say what we put in, and the output is what the computer gives us in exchange, we could say. So it is what comes out. And so these two together are sometimes called input output, and they're read in IO. And in fact, in many programming languages, when you include libraries to do input output, such as in C++ IO stream, or like in standard C, stdio, and so sometimes it is abbreviated as input output. And we will see that these libraries such as IOStream and stdio actually work on a lower level, so by giving output on the terminal, by communicating with the kernel by syscalls, and assembly actually communicates with the kernel in order to communicate, for example, to do input output with the terminal using syscalls. In x86-64, this is called, for example, for input. And in the next videos, we will see how this works more in depth. But for now, let's just mention this. The third part of our architecture is called memory. And memory basically is, I'm sure you're also a little bit familiar with the concept of memory in a computer. Maybe you've also heard about the distinction about secondary and primary memory, also known as volatile and non-volatile memory. And well, the volatile memory, and so let's give the distinctions of the type of memories. We have mostly two types of memories, that is volatile memory and non-volatile memory. So what does this mean? Volatile memory is just the memory that gets erased whenever, this is in very simple terms, whenever we shut down the computer. And so, for example, this is the RAM, the memory in the RAM, which is an acronym for random access memory. And the non-volatile memory, on the other hand, is in the memory that the computer stores even after we shut it down. And this is often achieved with electromechanical memories or with optically accessible memories. Two examples of non-volatile memories that are very common in modern computer architectures are, for example, HDDs and SSDs, where HDD stands for hard disk drive, and SSD stands for solid state disk. And for example, HDDs work using magnetic fields, and whereas SSDs, for example, work using charge trap flash memory cells and basically storing bits inside the memory by adjusting, we would say, quote unquote, adjusting electron levels. But we won't dig deep into this, also because we don't really need it at the moment, but just for an example. And then maybe for some of you, these two components might be new, but for now, just know that these that control and data path are actually done by what is known as the CPU, which is an acronym for the Central Processing Unit. And the control operations done by the processor as the commands that the processor gives to the computer, whereas you could see data path as the component that does all the, we could say, heavy calculations. And so this is a quick overview of the five basic parts of a modern computer architecture. And now you might say, but how are these parts interconnected? So how do they work together? So this brings us to a more high-level visualization of the von Neumann architecture. So let's draw our computer as a box. Okay. Now, let this be our CPU. where we know there's a control unit, and then there's a data path unit. We can say control and data path. So we also said that our computer has memory, and our memory basically communicates with the CPU. Then we will also see that there are a kind of immediate memory that the CPU can access that are called registers. Let's include them there. So we can see, we can call them R, but we will see what registers are later. So for now, just know that the CPU communicates with memory, and this memory is both volatile and non-volatile memory. And so how does a computer work? Very simply. So this is our computer, and then us, when we insert an input inside it, the input that our computer receives will be processed by the CPU and all the components, and it will yield an output as a result. So this is fundamentally how a computer works. It is a synergy of various components. Now that we have a basic high-level view, let's start to just go a little bit deeper, but just deep enough that will be basically useful for our assembly journey, we could say. So one other question could be like, how are these components connected? And well, I'm sure you've heard this term also, but what makes communication between these components possible is the motherboard, which takes basically its name, is actually a shorthand name for the mother circuit board, or also known as the main circuit board. Because what does it do is basically it's a circuit board, which I'm sure you've probably also seen in your computers if you've ever assembled one yourself. And then what happens is you have all the components put on it, and then they are connected via some connection that are known as bus. And this is on a very high level how the motherboard works. So for now, we have a very simple understanding of a computer architecture. So what we have is our CPU, which we can see as the brain of the computer, that then communicates via the bus with all the other components, which we've seen is the memory. In particular, we've seen the random access memory, so the RAM. It communicates with the non-volatile memory, so we could say HDDs or SSDs or other types of non-volatile memory. And then it also communicates with the outside via input-output devices. And the most common input-output devices that you've surely used are, for example, keyboards and mouses for input, and maybe screens for output. And this is on a very basic level how a computer works. Now that we understand on a basic level how computers work, we now ask another question. So far we understand that computers basically have all these components and whatever, but how do computers execute programs? How do operating systems work? All this stuff. And well, all of this is made possible by this so-called stored program paradigm. And what it means is that, well, in the last videos, we already talked about that computers only understand zeros and ones. And these zeros and ones, of course, can be used to codify information, because we know that a binary system can be used to express all the integers we want. For example, this is 1 plus 2 plus 4 plus 16. Well, when we will talk about the ASCII codification of the alphabet, we will how binary digits can be used to codify codify letters. But what about, so this is for data, however, but what about programs? And well, it turns out that not only data, so again, letters and numbers, and actually also images, because images are nothing but, like contiguous pixels, but a pixel is given by 3 values, and that is a value for red, a value for green, and a value for blue. And these are, each one of them has a value that is represented by 8 bits. So a value between 0 and 255 in decimal. And basically, so also images can be codified as arrays of these triplets of 8 bits. And so we now understand a little bit how computers deal with data, but how do they deal with programs? And well, it turns out that programs, just like data, can be stored in memory if we associate to some binary sequences some instructions. And this, again, we talked about in the first video, is very dependent on the architecture of your computer, and also the number of bits that are allocated in order to represent an instruction also depends on the architecture of a computer. For example, for a 32 bits computer, architecture are represented as 32 bits, so as sequences of 32 binary digits, which is zeros and ones. Now suppose we want to add two numbers, for example 16 plus 17. So 17 in binary is just equal to 1 0 0 0 1, whereas 16 is equal to 1 0 0 0 0. So can we add them? How can we tell the computer in machine code to add these two numbers together? And we will see that that's specified in the MIPS architecture, because as we said in the last videos too, because instructions of course changes between architectures. So how do we do this? Well, we start by telling the computer which operations are we trying to perform, and this is done by adding some codes at the beginning and the end of the instruction. And for addition, this is a 0 0 0 0 0 0 0, which is 6 bits at the beginning, and 6 bits at the end, which is on the other hand 32 in decimal. So by adding 0 at the beginning and 32 in binary digits, of course, we tell the computer that we're trying to perform an addition. But now in the middle, which is in all the other fields, because remember we have 32 bits available in this because we're considering a 32-bit architecture, we now put the operators inside. And the second field, which we're going to reserve 5 bits, in this case, and 17 is actually 5 bits, it's 5 binary digits, we're going to give the first operand. Well, we said 16 plus 17, so let's give 16, which is 1 0 0 0 0. Then in the third field, we're going to give the second operand, which is 17 in binary, and that is 1 0 0 0 1. The fourth field will be the we can call this the register, where we will save, so we can say the destination register. And then the fifth field in this instruction is left unused, but there are many other cases where we use actually all of the fields for an instruction of 32 bits. And so now we understand how instructions can be written using binary digits, and we now understand the program, which is a series of instructions, so we can say like 0, 1, whatever, and then other blocks of 32 bits which represent instructions if it is saved in non-volatile memory. And if the computer has access to it, then the computer can execute it just by executing each instruction. But now with this said, you should understand how computers, how you can codify in binary instructions for a computer. But there's maybe just one word that is not entirely clear to you now, and it's actually supposed to be that way because we haven't introduced this concept yet, and that is of a register. So we mentioned already that a register is a form of memory, but what is exactly a register? So this is why we will now dig deeper into the concept of memory, as well as the various types of. So we said that there are various types of memory. So we have volatile memory, which is RAM. And by volatile, we said already that we mean that when we shut down our computer, the stuff that is on the RAM gets erased. And then there's the non-volatile memory, that on the other hand keeps the data stored inside the computer. So let us give an example of something that might be saved on non-volatile memory and something which could be saved on a RAM. So for example, on the RAM might be saved the values of some variables inside our program. So for example, if you're familiar with C, then if we declare like a variable b to be of integer type and we set it equal to 2, then the value of this b will be saved inside the RAM. But what about stuff that can be stored inside non-volatile memory? Well, one example might be an image that you downloaded from the internet that you saved on your computer, then you shut it down, the next day you still have that image on your computer. So an image can be an example. Or for example, your program, which for example could be main.c, or maybe, I don't know, if you're writing like a scraper in Python, scraper.py. Or maybe if you're writing another sort of program in another language, or maybe, for example, if say you're implementing chess logic in Java, that could be chess.java. And so your program, the code that you wrote gets stored on your non-volatile memory. Because, well, if you write a Java program, you save it, and then you shut down the computer the next day, you still have that Java program inside your computer. So now it should be pretty clear to you what the RAM memory and the non-volatile memory on an high level of abstraction do and how they work. But we also mentioned register. And well, what a register is, it is just a temporary store. And you might say, well, why do we use, for example, register? Well, because in this small, we could say, hierarchy that we made, it turns out that the more we go upstairs, the more the speed to access a value will be. In fact, if you want some more, we could say quantitative data and not just qualitative. To accessing a value from a register usually takes around 1 or 2 nanoseconds. So it is around the order of a nanosecond. But for example, accessing it from the RAM, from the primary storage, also known as volatile memory, it usually takes up to 100 or 150 nanoseconds. Whereas for the secondary storage, which is also known as the volatile memory, as the non-volatile memory, it usually takes a time of the order of milliseconds. So 3 or 15 milliseconds. And as you can see, the time difference is huge between a register and a non-volatile memory. So for this reason, when we do computations and other things where, well, of course, performance is critical, we of course do operations between registers. And so, however, all these types of memory actually obey to a very important law of project management, and that is that, well, the faster a thing is, of course, the more expensive it will be. And so not only, well, of course, they will be faster, but they will be more expensive, of course, in terms of expensiveness in terms of implementing them inside the computer architecture. And this is why, for example, we have the RAM that in most computers nowadays is around 16 or 32 gigabytes, and we have secondary memory that nowadays in most computers is the order of a terabyte. But a register, in most CPUs, we just have 20 or 30 registers of, depending on the architecture, that can store 32 or 64 bit. And so we can already see how the more the speed that we have by accessing something, well, the more the expensiveness, of course. And so we are now ready to the point of start talking about the type of architecture that we will focus on in this assembly series, and that is the 64-bit architecture. So, because of course CPU registers, depending on the architecture, can store a variable amount of bits. So in the 32-bit computers, the registers will store 32 bits, whereas in a 64-bit computer, the registers will store 64 bits. That means 64 zeros and ones. So you can understand that the highest value that we can put inside our register will be equal to the 64 minus 1. Well, notice that this is for unsigned integers. So in other words, if you specify that we do not care about the sign of an integer, then the biggest value that we can store inside a 64-bit register is 2 to the 64 minus 1, which you can compute it when maybe with a calculator right now, and you can see that it is a pretty big number. And then for signed values, on the other hand, inside a 64-bit register, the biggest value that we can store is equal to 2 to the 63 minus 1. And the reason why we lose 1 bit, as you can see from 64 to 63, is because of the sign flag. In fact, 1 bit, that is 1, 0, or 1, will be devoted to telling us if we wish to interpret that number as a positive or as a negative number. And we will see how this works more in depth when we go into assembly specifically. So now we understand what a register is, what is the maximum size of a number that can be stored inside a 64-bit register. Let's now start seeing at the various types of registers that we have. Because inside the CPU, we have many registers, and most of them are actually general purpose. What do we mean by general purpose? Well, it's pretty obvious, but let's still define it. It's just the types of registers that can be used for everything. So basically, they don't have a specific use. For example, these can be RAX, RDI, RSI, and we will see what these names. Don't worry about these names for now. These are just the names of these registers, and that we will use in our assembly programs. Even though, be careful that even though these are general purpose registers, when we will be interested in making syscalls to the kernel, sometimes we will have to put these registers to some specific values. But this does not change the general purposeness of these registers. It just means that we will have to adjust them in order to give some information to the kernel or other stuff. But as well as there are, general purpose registers, there's also registers which have a specific goal, and they just do that, basically. One example of such register is the register called RIP. Another register is RSP and RBP. So let's now explain what each one of these registers does. So the first register, RIP, stores the next instruction that needs to be executed. So stores the next instruction to execute. And so we call this the instruction pointer register. Whereas RSP and RBP have to do with stacks, and RBP also with functions. And RSP points to the top of the stack, which we will see what the stack is. It's basically, well, the stack in computer science in general is a data structure, but in the case of memory, we basically, in our programs, we store memory by pushing stuff to the top of the stack, and the stack lies on in the primary memory, of course, and by pushing stuff on the top, and basically the RSP pointer points to the top of the stack, so that when we push something to memory, and imagine we push something else, maybe up here, then the RSP points at the new top of the stack. But if when there's this other operation that I'm sure you've heard of if you ever studied some data structures and algorithms, and that is if we pop this value inside a register, maybe RSI say, so we remove it from the stack, then the RSP pointer starts pointing back at the top, and the RSI gets the value of the old top of the stack. And well, on the other hand, what the RBP pointer does, it basically, on the other hand, it points still to a position on the stack, but at the base of a function. And what we mean by base of a function, it kind of, we can see it as taking a snapshot of the stack and then storing it. Sometimes programs will run what is known as frame pointer omission. And what basically this does is basically frees the RBP pointer from its, we could say, duty. And inside that program, you will be able to use RBP as another general purpose register. And what the RBP pointer does, we will see it later more in depth. Now, for now, don't worry about it because it's a little bit difficult to explain before talking about precisely how the stack works and how assembly programs work in general. So, and now that we have talked about registers, we also mentioned the names of these registers. And however, inside our assembly programs, sometimes we will only be interested in a fragment of the register. So know that our register, that can be RAX, RCI, whatever you want, is 64 bits long. But sometimes we might be interested in a fraction of it. So for example, we might be interested in only 32 bits. Or sometimes when you only need to do some basic operations only on 16 bits, or maybe sometimes even only 8 bits. And so how do we work with only this small fragment? And the answer is we basically take the lowest part of our register. And the lowest parts of a register have different names. So let's look at the names for the RAX register that we talked about earlier. So RAX register is just a 64-bit register. So you can see, so you can imagine it as being the string of bits that is 64 bits long. So now, if we take the lowest 32 bits, the name of this lowest part of this 32 bits register is called EAX. And actually, the name EAX is just an acronym for extended AX. And why? Because if we take the lower 16 bits of this register here, EAX, so this other sub fragment that we can, maybe let's denote it with another color, that is 64 bits, then this is called AX. And again, if we want an even smaller subset of our register AX, we can take the lowest 8 bits of our AX register, yielding AL. And this, we could say, naming convention is also kept with other registers. So for example, if you have RBX, that is again a 64-bit register, then the lowest 32 bits portion, you guessed it, is named EBX. And the lowest 64 bits of this EBX register is BX. And if we take only the lowest 8 bits, so let's call this 8 bits, then we just get BL. And again, it's the same with RCX. Let's not just write we could say, let's not draw the visual representation again, but then we get just, this is 64 bits, then for 32 bits we get ECX, for 16 we get CX, and then for 8 bits we get CL, and so on. And so this is very important sometimes when we will want to work with less bits than the full register. So with this said, I think we have said enough for now, and in the next video we will actually start by installing the assembler to start writing assembly code. And